So my project is vibration response estimation using a PIN. And aerospace components often experience high levels of vibration. This can be due to turbulent boundary layer changes in those, and engine noise as well. Right, and this can cause fatigue failure or electrical malfunction of components. For example, this pipe is a crack is formed and it's failed, and that's been due to prolonged exposure to vibrations. So, if the response is known at a particular location, then you can predict component failure. Um, but the challenge is that measurements are sparse, right? Typically, flight environment data is not super available because they're expensive, and you don't have a ton of accelerometers. So what I wanted to know is, can a neural net predict unknown responses? For example, at these red locations, given these blue locations, um, more accurately than traditional methods. So, for the methodology, the input are measured physical responses, and in these cases, I used displacements. And each sample is a time step, or rather, a set of displacements for the measured degrees of freedom at a time step. So the number of batches in total is the number of time steps, and the experimental or analytical data is down here, and it's just time series displacement data. This case, I did it analytically, though in practice, you would have it from an experiment. So then the output of this model is modal responses, which are these cues here. And you then put those into this physics-informed loss, x minus VQ norm of that squared. Where I get this loss from is the equation x equals VQ, which suggests that a set of physical responses is a linear combination of some mode shapes times some mode responses. And that's kind of the fundamental equation of the theory of linear vibrations. So you calculate the L, then you backprop it to get the gradient with respect to the weights, update those weights until they converge, and then the weights and biases and all the parameters. And then you estimate the unknown responses using your cues and some set of mode shapes at the unknown DOFs, where you would know these mode shapes from a model. So essentially, I started with a 5 degree of freedom mass spring damper system. I started with something simple to validate the method. So I assumed that you would know the responses on the first four masses and that you're trying to estimate the response on the fifth mass. Now, in this case, of course, we actually know the response of all of these. Hence, we can compare or see how accurate the method is. But in practice, you wouldn't know that response. So I generated these responses analytically. I just did the analytical solution for a free response, and I just did a single response for these four masses. Was the training data, at all the time steps that I calculated it at, which I think was like around 2,500 time steps, and pretty well included the start of the response to the decay, or when it about reached steady state, or about reached zero rather. So I use these sets of parameters for this case, four inputs because four measured responses, two outputs because two modal responses were included in this model. In practice, you could have an idea of how many modal responses there were from a finite element model. It'd be a bit messier, but you could approximate it reasonably well, presumably. Use ReLU, the atom optimizer, and that step size in 5,000 pixels. So I found that the model converged very well in 5,000 epochs, below 10 to the -6 L2 error. I found that the modal responses, these cues here, were recreated very accurately, as you can see. And as a result, the displacement of the fifth degree of freedom, or the fifth mass, was recreated very accurately as well. All right, so this proves that, the method works basically. But this isn't a very useful case. So for the second part of my project, I wanted to investigate a more useful case. In particular, I wanted to see if a PIN would yield more accurate results over the traditional modal filter method when the mode shape matrix is ill-conditioned. So traditional modal filtering is you just take the pseudo inverse or the left inverse of the mode shape matrix, and you multiply it by your vector of measured responses to get the Qs. Now, the problem is that sometimes the phi matrix is ill-conditioned. That can happen when you don't have many accelerometers or when accelerometers are placed at bad locations. And when phi is ill-conditioned, the Qs are very sensitive to any noise in X. And obviously, you're going to have a good amount of measurement noise for accelerometers in flight. So essentially, you can calculate Qs really inaccurately using this approach, and you can get a lot of error in estimating the unknown response. So I wanted to see if a PIN would be more robust to ill conditioning. So I used this finite element model, generated 6 responses at these locations in blue, where each blue circle is a triaxial accelerometer. Then I applied the modal filter and the PIN to generate the modal responses. In this case, I included 3 modal responses, so that's the number of labels in this case. And then I used those Qs to predict the unmeasured response at this red arrow location in the tangential direction. So essentially, the parameters are the same as the mass spring damper case, except the number of features and labels has changed accordingly. As you can see here, the loss converges, or is very low after 5,000 epochs, and the Qs are recreated pretty accurately, though there's a little bit of it. And as you can see here, even that kind of fairly small amount of error, and even though that we got the model to converge and to get the training error small, we see that the displacement response is quite a bit of error. The actual response is in black. The modal filter or pseudo-inverse approach is shown in orange, and then the results of the PIN are shown in teal. And essentially, it's kind of hard to see from this plot, on the left, which is more accurate. So I just calculated the absolute value of the difference between, the actual environment and either of the predicted environments at each frequency line or at each time step rather. As you can see here on the right, the PIN actually pretty consistently has slightly lower error than the modal filter. So essentially, the PIN, is more accurate, which is cool. Um, Now, you might be wondering, well, the results are still pretty bad for the PIN, and that's certainly true. And I think that's because this is kind of a really hard problem to solve, right? Ideally, you could just get more accelerometers and have a better conditioned accelerometer set. Um, but in this case, when it is ill conditioned, just any small error in the lower responses, can really cause significant errors. And so it's kind of a problem that I don't think there's like a great solution to. So that's why I think, the PIN still isn't wonderful. But it does appear to be, a little more robust still conditioning, right? The condition number of the mode-shaped matrix is about 100, 1 divided by 0.01 there. So essentially, right, yeah, I think this suggests that the PIN is more robust still conditioning. I didn't expect this to happen because you're using the same loss function, right? The pseudo inverse is the analytical solution that results in minimal least squares error. Um, so I would have thought you'd get the same thing, but I believe that because you've nonlinearities in the PIN, that means they're more robust than just the linear least squares solution in the pseudo inverse. So essentially, to conclude, I used a PIN to predict unknown vibration responses so that you could prevent things from breaking and change designs if needed. I used a mass spring damper case study and then a FEM. And then I found that the PIN recreated unmeasured responses more accurately than the traditional modal filter pseudo inverse. So this could be, a pretty useful technique in the aerospace industry to validate model design and predict failure. Of course, it needs a bit more testing and time. But I'm really encouraged by the results of this and do think it could be really useful. And with that, thanks for watching, and that'll be all.